Hey there, ladies and gents. Mr. Dickin here with our latest installment of Polynomial Fun. Today we are going to be solving polynomial equations. So that entails we will be seeing the equal sign popping up. So a few properties to go over first, and then we'll jump into some problems, and I'll show you some factor patterns to keep a lookout for. First off, a polynomial of nth degree will have at most n minus 1 turning points. So what that means is if I have, say, x to the fifth power, then I would have at most 4 turnaround points. I'm not guaranteed to have 4, but I'd have at most 4. So for instance, if I came up from the bottom left, I've got 1 turnaround points, 2, 3, and 4. So this is maybe an example of what an x to the fifth could look like. The next part is really the meat and potatoes here. And that says a polynomial of the nth degree will have n solutions. And this can be split between real and imaginary values. So real solutions, basic numbers, maybe fractions, or square roots, radicals, things like that. And imaginary, typically you'll see the letter I showing up with those. So let's get into factoring review here, because we're going to use factoring a lot when it comes time to solving these. Always, first off, look for a GCF, right? That is a greatest common factor. Can we shrink the numbers down? Then you want to see if maybe there's a pattern that we've already covered hidden within there. So for instance, difference of squares. If I saw, say, 4 minus 9x squared, well, I could factor that into a 2 plus 3x and a 2 minus 3x. And I could go through and solve from there. I'm going to switch over to black ink because this pink is looking a little faint. Or we've got problems dealing with, say, trinomials. So if I had, say, x squared plus 7x plus 10 is a trinomial because it's got 1, 2, 3 numbers, 3 terms, hence trinomial. And we could factor this into, let's see, x squared breaks down into x and x, 2 numbers that multiply to 10 but add up to 7, positive 5, positive 2. So those factor patterns might pop up along the way. We need to make sure we are aware of those. Today we're going to learn 2 new ones. As we go through these, as always, if there's any part where you feel like you need to pause it, please feel free to do so. All right, so I've got 4 examples here. This is going to be the technique if you have a 4-term polynomial, and it's going to be factored by grouping or factor by pairing, you might sometimes see. You'll notice we're going to be finding real and imaginary solutions for each of these. This one starts with an x to the third, which means I should have 3 answers. X to the third, I need 3 answers. X to the third, I need 3 answers. Down here on number 4, x to the fourth, I'm going to have 4 answers for this one. All right, so step number 1 is always going to be a GCF. Number 1 does not have a GCF. Cool, step number 1's done. Now I'm going into my factoring. So what I'm going to do is I'm going to factor by grouping. So I'm going to focus my attention first on this pair of values. So I'm going to focus on x to the third and 3x squared. So let me kind of cover up the rest of it. I'm only focusing on that bit. Do I have a GCF there? Well, yeah, I've got a 1x squared. And if I factor that out, I'm left with x plus 3. Then I'm going to focus my attention over on to the second portion. I've got a negative 5x and a negative 15. So I'm going to throw the parentheses around here, but I'm actually going to include the negative. And the reason for that is if I ever start off with a negative term, I'm going to want to factor out that negative value. So I'm going to factor out a negative 5, right? And I'd be left with x, and then this turns into a plus 3. Now, right now, I can kind of predict that I'm doing it correctly because right here, these 2 parenthesis chunks match. If those don't match, I've probably made a goof somewhere, and I'd have to go back and find the goof. So now what I can say is, well, both of these have a common factor of x plus 3. So I can have an x plus 3 pulled out of each one of these terms. And then I'm going to have the leftovers, which was an x squared and a minus 5. X squared minus 5. So I've taken this original problem and now I've factored it. Well, now I just have to solve each one of these little equations here. Either x plus 3 equals 0 or x squared minus 5 equals 0. So I have two small equations here to solve. For the first one, just subtract 3. So I'd get x equals 3. For the second one, I'd have to move the 5 over and then square root it. Square root of 5 is not pretty, so I'll just call it the square root of 5. But I should have 3 total answers, and the reason for that is anytime I take the square root of a value, I have to make sure I'm including positive or negative. So anytime I toss a radical on here, I have to include plus or minus. All right, next one, we're going to go slightly quicker through it. First step, look for a GCF. There is none. Okay, so now we group them up. GCF of this first group, x cubed and 4x squared, well, that's just x squared, and I'm left with an x plus 4. So looking ahead, I'm kind of anticipating seeing an x plus 4 over here. If I look at this other group, a positive 3x and a positive 12, I can factor out a positive 3 from each of those terms, and I'm left with x plus 4. Sweet, so I'm on the right track. Since these both have an x plus 4, I can take an x plus 4 and factor that out from each individual term. X plus 4 times x squared plus 3 equals 0. So now I've written it in completely factored form. And now I have two equations to solve. For this one, I'd get x equals negative 4 if I said x plus 4 equals 0. And for this other one, x squared plus 3 equals 0, I'd have to move the 3 to the other side. And it looks like I'm square rooting a negative, so that's going to tell me there's going to be an I involved. So for this one, I'm going to have x equals plus or minus I rad 3, or rad 3I, as long as the I is not underneath the radical. Again, making sure I have 3 answers. I have 1 here, and then 2, 3, because that plus minus counts as 2 answers. For the sake of time, we will only do one more of these. Let's do number 3 here. Just as a heads up on number 4, we would have a GCF that we'd have to make sure we address first. And then we could go factor by grouping just on this central part here. All right, so number 3, let's see here. Ooh, it's not equal to 0. Bummer. We always like these equal to 0 because then when we break it down, it allows us to use the zero product property. So all I had to do is just scooch that 10 to the other side. Now we're going to group them up. GCF of that first grouping is an x squared, and I'm left with x plus 5. In the second group, negative 2x minus 10, GCF would be a negative 2. Remember, if it starts with a negative, I'm probably going to need to factor out a negative, leaving me with an x plus 5. This now factors down into x squared minus 2 and x plus 5. And then I solve each one independently. This would give me positive, negative, rad 2. So there's 2 answers. Then over here, negative 5. Excellent. One thing I should mention, though, on number 4, anytime you have a GCF of an x, that means that the final answer, that's going to result in an x equals 0. So just make sure we keep that in mind. Onward we go. Sum and difference of cubes formulas. Before we get too far into this, just like it's important to have the perfect square values memorized, you're also going to want to know perfect cubes. So this row of values here, you're just going to want to have these in the back of your mind at all times. If you ever see one, it should set off a little light bulb for you. So 2 to the third power is 8, 3 to the third power is 27, 4 to the third 64, 5 to the third 125. So once you have these down, in order to use this pattern, the sum and difference of cubes, we have 3 criteria that need to be met. First off, binomial means it has to have 2 terms. Subtraction or addition sign, so no multiplying, dividing, has to be either something plus something or something minus something. And both terms, both terms are perfect cubes. So the formulas are as follows. And if you need to pause this to write this down, I would strongly advise it. If you have the sum of cubes, it's going to break down into the cubed root of your first term plus the cubed root of your second term. So we have to establish what are those cube roots. Then we're going to multiply that by the quantity where we square the first term. And then the last one is going to be the square of the second term. And in the middle is going to be the product of the two. You'll notice both of these formulas say the exact same thing. The only difference is the symbols in between them. And the little study tip you can use here is SOAP, same, opposite, always positive. So if I have a plus sign, the first symbol is going to be the same as that. The second symbol is going to be opposite, so this was a plus, so that's a minus. And the last term is always positive. Same thing down here. If this is a minus, this would be the same sign. This would be the opposite sign, and this is always positive over here. So let's see some examples. Again, in the interest of time, we'll probably only do maybe 3 of these. So let's do number 1 here. X cubed and 8. Well, I know 8 from the list is really 2 to the 3rd power. And x cubed, well, that's just x to the 3rd power. So I'm basically getting my a and b values here. If a is x and b is 2, then a cubed is x cubed, and then b cubed is 2 cubed, or 8. Well, now I can go into my factor patterns. If I follow my SOAP, this is a plus sign, so we go same, opposite, always positive. The first term's here. This is going to be a plus b. Well, we just said a was x and b was 2. This next term is going to start off with an a squared, so x squared, because again, my a value is x, and it's going to end with a b squared. Well, 2 squared, that's 4. And then we're going to have left the product of the 2, so 2x. And now it's been factored. Over here, we are going to figure out our a and b values. Oh, you know what? And I just realized it says we should have an equation, so this should be equal to 0. Hey, my a value and my b value have to be the cubed roots of these terms individually. So my a value is going to be, let's see, what cubed is 27? That's 3 cubed, and then we have an x. And then 1 cubed is just 1. So if I go into my parentheses setups, remember SOAP, same, opposite, always positive. So same, opposite, always positive. My a value was a 3x, my b value is a 1. My a value for this is a squared, so a was 3x. That means this is going to be, let's see, 3x quantity squared is 9x squared. 1 squared, well, that's easy, that's just 1. Then in the middle is the product of the 2. 3x times 1 is just 3x. Let's get the bottom ones set up by factoring. Ooh, number 3. We've got a GCF here. GCF is 2x. 2x goes into both of these, so I can yank out a 2x, and I'm left with x to the 3rd minus, let's see, that'd be 8. Well, this is going to look pretty much the same as number 1, just flip-flop the signs, right? X cubed plus 8, x cubed minus 8. So we're going to have, switch colors here, 2x, and then x minus 2, x squared plus 2x plus 4. So now it's been factored. Now for each one of these, it's wanting us to solve. So we're going to assume that there is an equals 0 at the end of all of these. And we are going to save the solving for the following video. So look forward for a part 2 because I'm running low on time. If something didn't make sense here, you guys know the drill. Let me know, send me a question, shoot me an email, and I'll get back to you very quickly.